Now, I want to go through a real quick kind of derivation of this velocity equation for you from a vector algebra type standpoint, but realize that we can use calculus and get the same stuff a little bit more quickly. Let's assume we have a ball traveling in a circle with some radius r, and we look at it from the side. And this is our r here. So the ball is traveling. If we were to look at it from the side, it would look like it was just going back and forth, back and forth, back and forth, and that the distance from here to here was changing as it slid back and forth. That radius would be adjusting, and we can call our maximum radius, our maximum displacement, x sub 0. Now, as it moves around the circle, if we look at it again, now we're looking top down again. Our displacement from the side is this portion here, this x sub 0 cosine theta. As it travels around in this circle, our sideways horizontal displacement is going to be this x sub 0 cosine theta. Okay. Then the horizontal velocity, okay, if we look at this bottom diagram, remember our velocity is always tangent to the circle, so our velocity is going off at this direction like this. If we apply a little trigonometry to this, this angle here is a similar angle to this one here. They're the same angle. And so then the horizontal component of the velocity is v sine theta. In order to give it a one-dimensional direction, we're going to call it negative v sine theta, because in this case it's to the left, and we're going to establish that as our negative direction. So for this particular object, our horizontal velocity is negative v sine theta, negative v times the sine of that angle. Okay, now to put it in, and actually in this situation, again, that v, we can really call it v sub 0. So it's negative v0 sine theta. It's sine theta times the maximum velocity that the ball has. Which, if we think about it from a sideways perspective, when it gets to this point here, if we're looking from the side, that would be our equilibrium position. The entirety of the velocity is traveling to the left, so the entirety of the velocity is that v0 sine theta, and we have again our maximum velocity at that point, the equilibrium position. Now, last part of this. Remember from uniform circular motion that the velocity is distance over time, but for a circle, we're talking about the circumference over the period. We have 2 pi r as our circumference over the period. Angular momentum, 2 pi over t is angular velocity, so 2 pi over t is equal to omega. So if we plug that in, when we're talking about simple harmonic motion and oscillations, our velocity is equal to omega r, where r is the radius of that circle. The radius, as we talked about, is the maximum displacement that that object's going to have, and so velocity is equal to, or really, let's call this v0 is equal to omega x sub 0. So the maximum velocity that an object's going to have in simple harmonic motion is the angular frequency, omega, times the x sub 0, the amplitude. If we plug this into our equation that we just found, v equals negative v0 sine theta, then we get v equals negative omega x sine omega t, and again the omega t, let's see, negative omega x sub 0 sine omega t. And the omega t is just our radians expression. Okay, so just to, primarily because it's so hard to read on here, our velocity in, our maximum velocity in simple harmonic motion is omega x sub 0. As we found from our derivation, v is equal to negative v negative v. Why aren't you? We cannot erase. That's okay. Negative v sine theta. So v equals negative omega x0 sine. We're going to convert this to radians, so that's omega t. So we have sine omega t. And that's our equation for the velocity at any point in our simple harmonic motion. Another look at this from a trigonometric perspective. We know that one of our trig rules is that sine squared theta plus cosine squared theta equals 1. And so if we rearrange that, we can say that sine theta is equal to the square root of 1 minus cosine squared theta. And if we multiply both sides by omega x sub 0, we get the expression you see there. And if we substitute our omega t in for our angle, then that gives us a slightly longer expression, which you can see in step 4. And if we pull our x sub 0 into the square, or pull it under the radical sign, we get omega x sub 0 sine omega t equals omega times the square root of x sub 0 squared minus x sub 0 squared cosine squared omega t. This seems like a very long, bulky equation, but remember that for our displacement equations, x sub 0 squared cosine squared omega t is simply equal to x squared, which is our displacement squared at any given point. So what that ends up doing for us is giving us a velocity that's equal to omega times the square root of x sub 0 squared, that's the amplitude, minus x squared. So this tells us that at some distance x from equilibrium, our object is going to have a speed, really, of whatever this calculates out to be. And the reason it's a plus and a minus is because depending on if it's above equilibrium or below equilibrium, it's going to either have a positive velocity or a negative velocity. This is just telling us what the speed is going to be that particular distance from equilibrium. It doesn't tell us whether it's above or below. And that's an important distinction. Okay, and then our last part of this is our acceleration. And again, just like with regular kinematics, the slope of our velocity graph gives us the acceleration. And so at any given point, our gradient of our velocity time graph gives us the acceleration. And if we look back here, we can see that our acceleration graph is phase shifted from our velocity graph by pi over 2, and it's phase shifted from our position graph by pi. So it's 180 degrees out of phase from our displacement graph. And so when we have our maximum positive displacement, we have our maximum negative acceleration, and vice versa. But in both situations, when our displacement is 0, our acceleration is 0. And that's that whole idea of as it passes through 0, as it passes through the equilibrium position, the acceleration is 0 because the net force is 0, but it's also where the velocity is at its maximum, and you can see that from this graph. So, at A, we have the maximum slope on our velocity graph, which means that we have the maximum acceleration. And if you remember from our graph, it looks like this. And then this green one is our velocity. When the velocity is at its maximum, our acceleration is at 0. Okay. When our velocity is at 0, our acceleration is at its maximum. Come up here, our velocity again is at its maximum, and so our acceleration is 0. And then our velocity is back to 0, and our acceleration is maximum in the positive, or in the opposite direction rather. Okay. Again, gradient of velocity time is our acceleration. And then our acceleration expression, the acceleration at any given point is equal to negative a sub 0, which hopefully we're catching on that subscript 0 means the maximum. So the maximum acceleration times cosine omega t. Again, that factor cosine omega t puts us somewhere along the graph depending on the time. The omega is our angular frequency. The time tells us how far along we are. Now, if we briefly consider our ball traveling in a circle, remember in circular motion, the acceleration is always towards the center. And so if we break this up into our components, okay, this angle here is the same as that angle there, and we have our a cosine theta. Again, it's in the opposite direction of the displacement. The displacement in this is in this direction. The acceleration is in this direction, so it's a negative. And so that's where the negative a cosine theta comes from a trig perspective. Putting in our centripetal motion, our centripetal acceleration is equal to v squared over r. We know that v is equal to omega r. So that gives us an acceleration of omega squared r squared over r, which simplifies to omega squared r. So acceleration is equal to omega squared r. We plug that in for our a, and that's where we get our equation for acceleration in terms of displacement and angular frequency. Acceleration is equal to negative omega squared x sub 0, where omega is, again, the angular frequency, x sub 0 is the maximum amplitude, and then omega t, again, tells us where along this is. So see from this that the acceleration at any given point is only dependent upon the angular frequency and the maximum displacement, the amplitude of the displacement. And so our maximum acceleration then is equal to the angular frequency squared times the amplitude. And again, notice that we have this negative sign here, which tells us that the acceleration is in the opposite direction from the displacement. And this is really the defining equation of simple harmonic motion. And it comes back to what we said at the very beginning. The acceleration is proportional to the displacement, and the two are related by the angular velocity squared. And again, the acceleration is always in the opposite direction of the displacement. Now, this is just for those of you who are maybe a little more familiar with calculus. All of the derivations using trig were just to kind of give you a little bit easier approach, but this is probably quicker and easier for many of you. If we differentiate, we can come up with these same equations much more quickly. Notice how we go from, and again, this isn't required now, you don't need to understand this or know this, but if you do, hopefully it helps. If we start here, and we can look and see our three main equations within each of these and a slightly quicker approach to reaching them. So just kind of an extra note for you if you like it. All right, that's it.